Okay, so I'm quickly going. I've had a slight change of mind, and so I'm going to quickly record just how to do regression and full factorials. So what I've done is I've created a covariate here we're going to use for regression model. So click specify second level model, and let's make. So I'm already in my location. So I'm already inside PWD. Cons for group level data for second level inside SPM course 2007. So if you're inside there, you can go inside cons for group level data for second level, and let's make a directory. So this is where we're doing the other group level models. So we'll create one called multiple regression, multi-regress. That'll do fine. Okay, so second level model we've clicked, so we've got a batch here. So we changed the design here to multiple regression. It'll ask us for our scans. So what we'll do is we'll take our placebo1 scans, select all. The directory, we'll select multiple regress. And now we need to put in the covariate. So in our case, it's going to be here. We'll just call it motor cortex. So what I've actually done is I've grabbed the activation from the same data from the motor cortex, and I've created a variable called cove, which points to it. So I'm slightly cheating. I'm going to be correlating its own data back against it, so we'll get a very significant result. So we can load a variable straight in, and that's it. So we'll do model estimation. So just to show you, actually, if you want to spatially constrain your analysis completely, you can still do it in another way, but I'm going to turn off the implicit masking, and I'm going to use an explicit mask to constrain it. Go into ROIs, and let's pick the pre-central gyrus. Okay. Save batch. Multi-regress. Pre-central mask, and we'll press play. It's going to run the estimation, and then we'll look quickly at the results. Yeah, it's 9 o'clock, and the lab is at 10. So I'm going to move through this quite quickly once. But the steps of results and everything are exactly the same as they were before. Oh, sorry, it's done. Okay. So as before, we click results, go into multi-regress, you pick your SPM.T, and you see this model. So this is the intercept of the model, and this is our covariate of interest. So our t-contrast is going to skip over the intercept because we don't really care about that. We want to find the brain regions which correlate with this. So positive correlation, or positive regression more accurately, but that's fine, is that, you can see. Select that, and we'll say apply masking none, no, ooh. Ooh, sorry, 0, give that, 0.001, only thing center, I don't say. And then hopefully, the region is massively, significantly correlated with itself. Okay. So, and of course, because we know there's interhemispheric connections, the left hemisphere also correlates. Even though they're using the right hand, the actual variation over time in the response does covary with the other side of the brain. Okay, so that's great, but let's say we want to plot that data. So one of the things you can do is you can extract the data here, and that will give you the mean for a cluster, or for this, well, actually it gives you all the values for all the voxels in the cluster, and then you have to calculate the mean yourself. It's not sensible to do this for any sort of analysis, but for plotting it can be useful. So you can click this, you get the value y out for that voxel. And that's the data across all 16 subjects for that coordinate. But let's go back quickly. So if we plot the data, but this time we don't want to plot, if we plot the confidence intervals, we'll get a single bar, which we don't really care about. In this case, what we want to do is plot the data against our covariate to see how strongly it correlates. So we plot against, predicted is before it's fitted, and adjusted is after fit of the model, so we want the adjusted. And we plotted against, if you plot against scan or time, you just get the values plotted against the subject scans. Okay, so that's what the value is. Not massively useful. But if we plot it against explanatory variable, and we pick our covariate, mean cortex, which is what we called it. So mean is just the intercept, and motor cortex is this covariate here. You see, the data is quite nicely fitting a line. It's a little bit ugly, but you can actually open the figure parameters and change things, or you can change stuff here like line width. I will change things, I think. Anyway, so you can change the plots a little bit in SPM, but it's probably not worth the hassle. You're better off doing file, save it as a export. Save as, and then change it to a JPEG or a TIFF or something, and then take it into Adobe Illustrator or something like that. So this can be moved around. Okay, and of course the converse contrast is possible as well. So negative correlation, 0, -1. Negative relationship. And there's nothing. Okay, so hopefully that's regression. Of course, the results and the thresholding are all exactly the same. So if you want to apply multiple comparisons correction to the maps, if we switch back then again to positive correlation. One thing I didn't show you before is if we turn on atlases, neuromorphometrics, you get a warning saying use atlases with great caution. But it does mean you can see, you can right click and it tells you this coordinate is in the left cerebral white matter, and it gives you these labels. So 43% of it is in the precentral gyrus, 2.6% of the postcentral gyrus, a little bit more. Whereas this coordinate here, I mean, again, we know this is all postcentral and precentral gyrus because we masked that area. So that can be useful for finding coordinates or labels in the brain. Yeah, and so multiple comparisons correction will be the same as always. So you just click set to FWE. That's the map corrected on the basis of cluster extent. If you set it back to 0.01, you read off here the K values. So the smallest K value is 349. So we'd set our extent threshold. So change 349. And that removes everything that's not significant. Again, you could just save that as a threshold at SPM, or save it as a binary image if you want to extract a signal or something like that. But again, it's important that your ROIs are generated independently of your data. Come back to me if you want to talk about that at any point. Small volume correction if you want to do that. Take an image, go into ROIs, pick the preset post-central gyrus, for example, even though. And there's nothing there because we masked it with the precentral gyrus, so that's not surprising. Whereas we pick here, image, precentral gyrus, and the statistics are all massively significant. Okay, so that's basically multi-progression. So we'll see where we are. We're inside multi-progress, so I'm going to move up, change directory one level up, make a directory called, mkdir. Full factorial. And as I said here, full factorial is just a multi-factor ANOVA. So we've talked about one-way ANOVAs being extensions of two-sample t-tests or paired sample t-tests for repeat within subjects ANOVAs. So we could expect second level. We can also specify slightly more complicated models. So let's say we've got a full factorial. So we've got two groups. So we've got one factor which is group, let's say. So let's go treat it as though we have two separate groups. and this has got 2 levels. Okay. And let's say we have one more factor. Let's say another factor. Oops, sorry, new factor. So click on factors. And this factor is going to be treatment. So we've got 2 groups, and they're then split into 2 groups to get different. Actually, let's not do 2 treatment. Let's do genotype because it's a bit more easy. It's a bit easier to understand in terms of them not being repeated measures. Okay, so again, there's 2 levels of it. We're going to treat our groups as though these labels apply. Now, you can tell in the full factorial, you can say that things are related, but actually it doesn't properly control for things the way it should. So it's best not to. So it's best to use a full factorial where you've got multiple between subjects factors, multiple groups basically within groups. So here we've got a group, and then the group splits. Let's say patrons and controls. And then we've got 2 separate genotypes, for example. In fact, we could even say we've got 3 if we don't have the data for 3, so we won't do that. You can have homozygotes in the 2 extremes, the 2 homozygote groups, and the heterozygotes in the middle, if you assumed a linear relationship. Okay, so if they're groups, they're independent of each other. The 2 groups, the 2 levels are from different populations, and therefore their variance is unequal. And this is explained down here as well. It's to do with how SPM deals with autocorrelation and non-sphericity of the error term, basically correlated variance. And the same thing for genotype. So we now have 2 factors, each with 2 levels. So that means we've got basically group 1, genotype 1, genotype 2, and then group 2, genotype 1, genotype 2. So there's 4 cells. So we create these cells. Cell 1, we already have. Cell 2, cell 3, cell 4. And again, if you select too many, you can go down here and delete them. So the first one is factor 1 of level 1 and level 1 of factor 1, so group 1, and genotype 1. The second one is group 1, genotype 2. The third one is group 2, genotype 1. And the next one is group 2, genotype 2. Okay, so we're just specifying that the scans we're going to give in these cases belong to these cells within an ANOVA structure. So now we're going to obviously treat our data a little bit differently because we've got placebo and drug. So we're going to treat the number here 1 as group, and the treatment as though as a genotype. So for group 1, treatment 1, so like that. And for genotype, for the same group but different genotype, we're going to take the drug data. So again, it's 1. For group 2, we're going to go to placebo 2. And for group 2, genotype 2, we're going to go for drug 2. And that's it, basically. We add on spatial, model estimation, dependency. And we have to obviously specify a directory, which is always the case. So we have a full factorial there. If we save this, and we execute, I'm going to pause this. Well, I'm going to pause it for a second just to. Okay, so is this recording still? Yeah, great. So that didn't take that long actually, and you can see it's done here. But one of the advantages of the full factorial is it creates some of the contrast for you. So let's look at these results now. So if we have a 2 by 2 factorial model, there is the average effective, which doesn't care. That's just basically saying, is there any, these are F contrasts first. Is there any voxels that go up or down on average across all 4? In fact, this is the sum of them, it has to be said. So it's the summing these together, any voxels where the sum of this or this or this or this beta is greater than 0. You don't really care about that. So the main effective group first, so compare these 2 summed together compared to minus these 2. That's what this contrast indicates. Then you've got the main effective genotype, which is this one and this one, so level 1 of the genotype, minus this one and this one. Okay, so these are 4 cells. 1, 1, 1, 2, 2, 1, 2, 2. So the main effect of genotype is to add the 2 genotypes together for genotype 1, and then the two groups together for genotype 1 and the 2 groups for genotype 2, and subtract them from each other. And the last thing then is the interaction. So it's where the difference between genotype 1 and 2 differs between the 2 groups. Okay. Now SPM also then creates T contrasts as well, which are directional rather than bidirectional in the F contrast. However, for some reason it only creates half the T's. So here's one of the T's, which is 1, 1, minus 1, minus 1, which is the T contrast direction of that. But it doesn't create the converse, which will be minus 1, minus 1, 1, 1. So we'll add those now. So we'll say minus 1, minus 1, 1, 1. So we'll say group 2 minus group 1. Because that's what it really is. We're averaging over these two, or summing together these two, and subtracting group 1 away from group 2. And we'll add the next one. This is genotype 2 minus genotype 1. Okay, and this is going to be, so this was going to be minus 1, 1, minus 1, 1. So again, it's genotype 2 minus genotype 1. And finally the interaction, so actually cancel that. So you see here they did the positive effect to group 1, positive effect to genotype, and the interaction, which is just the diff multiplying these two together, which gives you this. So we want to do the corresponding one, which is minus 1, 1. Minus 1, 1, 1, minus 1. So this is interaction. And this is saying basically the difference between the first genotype and the second genotype is different for the second group. Okay, and that's going to create the contrast. So say no, none, and say nothing survives correction, which is fine. Didn't really expect it to, but we then want to select our other things. It's going to create them. So no voxels survive the threshold. So basically, there's nothing significant in the map, which is fine. We didn't really expect it to be. So let's have a quick look, though. Flexible factorials. Let's just do the average. It's a bit slow. Very slow, in fact. Ah, there we go. Okay. So you can see the model does work, but just that there isn't any significance. So you can set for the main effective group as an F contrast, main effective genotype, and the interaction. And there's a very weak effect in the interaction, but it's not significant. Okay, so the last model to look at is the flexible factorial, and this is a much more complicated model. So I just want to show you, if you Google Glasher and Gittleman contrast weights in flexible factorial. This gives you the instructions for how to set this model up. They're almost correct. They just make one slight error, which is in this case where they've got two groups, each with three repeated measures, and the subject columns here, like in a paired t-test, they test for the main effective group. In this case, so they sum these three together and then subtract these three, for example, and that's inappropriate because the between subjects variance is modeled here. But let me take you quickly through the setup. It's described in detail in this handout. If you want to use this model, arrange to come see me and talk to me about it, because it's not the easiest model to handle in the world, and you'll see why in a second. So last thing we'll do is we'll go up one level, make a directory called flex factorial. and right, specify second level, and design flexible factorial. Now the principle is basically the same, except there's a couple of special factors, and they describe them here. Subject basically allows you to specify where the data comes from a single subject. And that's quite useful. It's a bit like a paired t-test. You're telling it these are repeated measures in the most appropriate way. So we'll set the directory, and we will, where's my flexible? Yep, there we go. So first thing I always do is create subject. Now the problem with this though is you end up losing one of your factors. You can do no more than a two-factor thing. So subjects are independent of each other, but their variance is equal because they're drawn from the same population. Okay, that's an important difference. Unlike group, which are independent, variance unequal, subjects are independent of each other, but they're from the same group, so they have equal variance. And this is explained in the PDF I showed you earlier on. So what we'll do now is we'll say we have treatment. There's one more factor, and the final factor we're going to put in is time. So we're going to treat our data the most appropriate way. Now, as it happens, these were 4 sessions. They're not really 2 different treatments. Well, they are 2 treatments and 2 placebos, but they're done in a one-way ANOVA really. But we're going to treat them like a 2x2. Okay. So the same subject, scanned on 2 occasions with 2 different treatments. That's 4 visits in total. And so treatment and are not independent. These are repeated measures, so it's the same subject. So we say independence, no, variance, equal. And independence, no, variance, equal. Because they're not independent of each other, they're the same subject, and equally the variance should be the same on both occasions. Okay, so then what we need to do is we need to put in the scans. And this is a bit of a faff, just like it was for a paired t-test. So we go to placebo 1, and then we are going to go with so this is treatment and then time. Oh, okay, fine. So then we go to placebo 2, drug 1, drug 2. And this is because our factor is time, so it goes 1, 2, and over here, treatment. So the level goes treatment 1, level 1, sorry, time 1, time 2, then treatment 2, time 2, time 1, time 2. So the idea is this, we're going through the level of time more quickly than we're going through the level of treatment when we're specifying it. So you can see here, it's group 1, so it's placebo, placebo, then drug, drug, but it's going 1, 2, 1, 2. So we're going through this, what's called the fastest rotating one is time, and the slower rotating one is placebo. That's a minutiae, it's not a big deal. And we specify that these are, we can forget factor the subject one, so it's, first scan is factor 1 of treatment and factor 1 of time, then factor 1 of treatment, factor 2 of time, then 2 of treatment, so second treatment, first time point, second treatment, second time point. Okay. Now I'm not going to do this over and over and over again, but we can just replicate the subjects till you've got 16. In fact, what we'll do is just replicate it again. Get across to 16. Okay, we'll come back to that 1 second then. And the last thing then you need to do is you need to build the model. So we've specified all this stuff up here, giving it the scans and telling which scans belong to which cells, and up here where we're specifying the factors and whether they're independent or not, basically establishes the internal structure of the model. But actually, you then have to build the model the way you want. So what I would typically do is include the main effective subjects. That results in you including the subject columns in the design matrix. So we say main effective factor 1. If you want to create a main effect of one of the other factors, that's fine, but they make very little difference. The biggest contribution here is the inclusion of factor 1, because you're modeling the between subjects variance, which is correct for between subjects for a repeated measure design. So you get a big increase in your t statistics usually. And again, this is described in the PDF. And we'll create an interaction. So that's going to be factor 2 and 3. So there's going to be treatment. Factor 2 is treatment. Factor 3 is time. Okay, so that's that. We'll leave all that alone. We'll add on stats model estimation. I'll put this here. Now, rather than I'm going to basically, because we haven't put in the right scans to begin, so I'm going to set up the script. Test flex for now, because I wasn't going to manually do that. I'm going to load up. So again, you can do exactly what we normally do with the scripts we did earlier. We're going to do this afternoon. You can save out the batch and script, and then you can change these numbers here. So this is going to be subject con1, con4. Yep. So this is going to be subject 2. So this 1.img. Fine, next. Let's replace it with 3.img. See, this is wonder of scripting and stuff, and especially if you're lazy like me. I wasn't going to do this by hand. I think I made this correct. Okay. And we can just save it here. Save, flex, batch, batch. I'll go for it now. So we have this flex batch here. Let's see if we can load it up. Batch editor. Okay, there's all the scans, and they've now been changed. Let me just check if that's correct. I probably should have checked. Oh, that is correct. Okay, I did check change the right number. Okay, so we can just press play, and again, I'm going to pause this while this runs because it can take a while. Okay, is the mic still? Yep, mic's still working. We're recording. Everything's fine. Okay, so that's finished now. So we can click on results. As you can see here, it's done model estimation. Click results, and we go to our flexible factorial. And you see here, this is the main effect of subject here. So the 16 subjects, so the 16 columns here, each one modeling the mean of that subject across the 4 scans. And these 4 columns here indicate the interaction terms. So they allow for us to ask a contrast, basically main effect of group, main effect of time, main effect of contrast. Sorry, interaction of the two of treatment or whatever. Now, because this is all repeated measures, it's fine to ask for the main effect of treatment or whatever. But if this was a grouping variable, then these between subjects variables would be important, and it would be inappropriate to model the data this way. If you had one of these factors was a group, you could run the model again, but this time don't add in the subject column, wherever I put it. Main effect. You take out this main effect here. You just delete main effect 1, and that would basically give you the same design, but without the subject column. So you just have this part here. Okay. The downside of the flexible factorial is it doesn't give you the contrast by default. So So we'll say main effect treatment is going to be 1, 1, actually it should be an F contrast, 1, 1, minus 1, minus 1. Okay, so that's the average of the first two visits versus the average of the second two visits. Sorry, first treatment over the 2 time points minus the second treatment average of the 2 time points. So you press done, and it's going to be the usual thing. Results. So no. And again, this is just the standard approach. And very little better. Okay. Then we have a new contrast. It's going to be the main effect of time. Sorry, again, F contrast. One minus 1, 1 minus 1. So again, we're averaging over time 1 for genotype, sorry, time 1 for treatment 1 plus time 1 for treatment 2, and we're subtracting time 2 from treatment 1 and time 2 from treatment 2. Okay? So this is the main effect of time averaging over the 2 treatments. And the final thing we add is the interaction term. 1 minus 1 minus 1, 1. Come on. And there we get the term. So you can see now this is the same data we modeled earlier on, but our significance has gone up massively. And in fact, this region wasn't coming through before with the paired t-test. So the flexible factorial is a big, I mean, we've modeled the same data as though it was independent variables, like separate groups, and the effects weren't there. But by including these subject columns in the model, we massively increase our sensitivity. You see, this is peak level correction. These are surviving cluster level correction, including this one here. And this one almost survives. Okay. And of course, you can then do those same contrasts as T contrasts. So, you know, 1 minus 1 minus 1, 1, interaction 1. And this will be even stronger because it's a directional test. We need to do the two interaction terms. You can see now it's even 0.05. So it's very, very significant. So 0.005, so it's even more significant. And new contrast, we'll do the converse as well. So we'll do interaction 2 minus 1, 1, 1 minus 1. Because obviously t-test is directional, so you have to do both. And there's nothing there. Okay, the only other thing to consider is if you want to create the effects of interest contrast. So if you remember, let me quickly go to the flexible full factorial for a moment. If you want to be able to plot the response, you need this effects of interest contrast that we talked about before. So the effects of interest contrast is just a 1 over each of these columns, but separated. So 1, 0, 1, 0, 0, 1, 0, 0, 0, 1. Okay? There's a shorthand for that, which is called the identity matrix. You see that? And of course, again, it's a bidirectional test, but it's very labeled. It's just asking, is there anything non-zero in any of those 4 conditions? So it'll give us most of the brain. Come on. Graphics is proving a little bit tricky today. It's slow. So far. Okay, you can see it's very, very sweet. Just to show you what the EY means, it's just the identity matrix. Interestingly, if you have a one-way ANOVA with 4 levels, the contrast to test for the main effect is the difference of the identity matrix. So it's minus 1, 1. Equally, if you've got 3 levels, so that's a shorthand for creating main effect. In fact, if you only have 2 levels, And that would be our contrast, 1 minus 1 if you had two groups. So that formula is a general formula, and there's a more complicated method for producing very complicated contrasts, which we won't talk about today. Okay, so the effects of interest contrast in that case is very, very simple. However, in the flexible factorial, it isn't, because each of these columns, the mean of it is distributed. The actual signal is a mixture of what's left over after you've subtracted the mean. But if you want to look at any one column in isolation, you need to add back the contribution from these subject columns. So EYE4 won't work here. However, if we do 1 and we skip over the next 3, each person contributes 1/16, because we've got 16 subjects. And this is sort of explained in the handout. They explain the idea of weighting by the subject columns, although they don't use the effects of interest contrast the way I do. So then the next one's 1,16. So now we can see we've got the first two conditions. This is 0, 0, 1, 0, 1s, 1,16 divided by 16. This isn't necessary, this is just a shorthand. You can use other methods for getting data out of the readers or quick plots. 1,16. 16. Okay, what are the effects of interest? And again, I'm going to show you the value of this contrast. Now, give it a couple of seconds to produce the image. Again, it's a very liberal contrast. We're asking if any of those individual columns is non-zero, up or down, so it'll give us pretty much all the brain. But what I'll show you then is how you can use that to understand what's driving the effects you're seeing in the interactions or in anything else. Oh, it's a bit slow, isn't it? Mic's still working, yes. Sorry, I'm doing a lot today. Don't think I'll use this system again for recording, it's a bit too nerve-wracking. Okay, so if you skip back then to your interaction, let's go to the p-coordinate. If you plot contrast sets with 90% confidence intervals and you pick the interaction 1, you'll get a single bar. But now, if you pick the effects of interest, this is what's driving our effect. So we've got placebo 1, drug 1, placebo 2, drug 2. So actually, the key thing here is that there's a massive difference in this region between the two placebos. And the drugs are actually doing something slightly different as well, but probably the biggest effect here is the two placebos are different in this area, which is a big problem. Okay, but that's just to show you that's how it would work. By using one contrast to find the result you want, but then plotting the effects of interest contrast, 90% confidence intervals. Okay, so hopefully that's useful. Don't worry too much about flexible factorial. If you're going to use one, come back and talk to me about it. But you have that Gittelman-Glasher thing you can search for, and that's quite a good explanation. It goes through setting it up. Okay, I think that's it. Yeah, we'll